Okay. So we're still in the section on functions. I did email you the notes. I also emailed the wrong set of notes actually. I also emailed you the notes from last week. I didn't get a chance to post it yet. Unfortunately, I had a lot going on. But what I did do at the very least is I emailed you the notes. So at the very least, you still have those notes. Let me just check something because there was a mistake in here last time. I just don't want to I want to make sure that mistake is not there again. It's okay. All right, let's get. All right. Anyway, I was just looking. I thought there was something I had to delete. Maybe I did delete it already, but so let's keep going. All right. Okay. So we're talking about functions in chapter 2. I'm hoping to finish this. If not today, then definitely Wednesday. Wednesday, I might give a worksheet as well, so people could try out doing questions on this. And what we're looking at here is domain of a function. Remember, the domain is by definition, it's all the input that can go into the function. In other words, for us, it's really all the numbers, the collection, the set of all numbers that go into a function that can yield a reasonable output. Okay? That's really what the domain is. Now, finding the domain from an equation, remember, you can have a function defined by an equation in x and y. Okay? What you do is you sketch its graph in the Cartesian plane, and if the graph passes the vertical line test, then you have a function. I mean, what you actually have is y as a function of x. That's what we've been dealing with. And again, the vertical line test, to pass the vertical line test, every vertical line that you can draw will either not intersect the graph or intersect the graph only once. So it's not like with a circle where you can draw a vertical line that intersects the graph twice. Okay, so if you have an equation and it's a function, it defines y as a function of x, you can still get the domain. I mean, you could get the domain from the graph, but you can also get the domain from an equation. Namely, what you do is you follow these rules that I have here, although 3 is really a special case of 2. So I probably didn't have to list 3 as a separate rule, but I did. But the denominator, you never want that to be 0. Okay? You never want denominators to be 0. You never want that. Because you can't divide by 0. Now, since we're not dealing with what's called complex numbers, you don't take the square root of a negative number. That's something also that you don't do. You never take the square root of a negative number. Okay? And for 3, if you happen to have the square root of something, that's something I'm calling it w. If you happen to have that in the denominator, I don't know what's in the numerator for now, it really doesn't matter. But if you happen to have the square root of w in the denominator, okay? The domain is everything such that the radicand, the w, what you're taking the square root of, in other words, is positive. So in other words, you want the square root of that, you want the radicand to be positive, basically, is what I'm saying, if this is in the denominator. If it's in the numerator, then you basically go by 2, and you just want it to be non-negative. You'll see some examples. It's probably confusing what I'm saying, but we'll see some examples today. And Wednesday on the worksheet, there'll be more examples. So these are just two examples here that hopefully will illustrate what I'm trying to say here. I mean, this one here, you want all x so that the denominator is not 0. In other words, so that x here is not 0. So the domain is all numbers except 0. This does define a function. We saw the graph last time. Okay. Here we have the square root. Now here it's not in the denominator of anything. So all we want is all x such that x is non-negative. We're taking the square root of x here. All x such that x is non-negative. Okay, and we can write that as an interval. Namely, we have this. 0, we have this interval, all numbers greater than or equal to 0. That's what I'm saying here as well. All x such that x is non-negative. Okay. Again, I did email you the notes, so just letting you know. Okay, let's do this example. So here we have this in the denominator, right? So what we want then is all x so that 2x minus 4 is positive. We're taking the square root of something in the denominator, right? At something, which is 2x minus 4, we want that positive. If it was not in the denominator, then you would just want it non-negative. But we want all x so that 2x minus 4 is greater than 0. Okay, so let's do that. So now we're using what we learned earlier from section 1.5. 2x minus 4 is positive. So we want to get x all alone, right? Okay, well, let's get the 4 out of here by adding 4 to both sides. Okay? Doing so, we get 2x is greater than 4. We get 2x is greater than 4. But we don't want 2x, we want x, so we have to divide. We divide both sides by 2, as you can see. And we get x greater than 2. Let me just say this also. We're not turning this inequality around. In other words, we're not flipping it. You only do that when you multiply or divide by a negative. And we're not doing that here. We're dividing by a positive, namely 2. So what we get is this, is this inequality. So the domain is all x such that x is greater than 2, which is the same as saying this interval. So all numbers bigger than 2 form the domain of this function. So if you plugged in any number from here, you would get an output that makes sense. In other words, you take anything from this interval, you plug it into x, you would get a real number as an output. I hope that, are there any questions about that? Before we do more examples, here are some certain special functions that you will see in mathematics. Polynomial functions, you see a lot of these. And this is a function of this form, a polynomial function in x. Basically, this is just a function, okay, that's equal to a polynomial like this. Okay? Namely, here, the n, okay, is the degree, remember? These a's with these subscripts are just fixed, they're just, constants, almost like complex numbers. Although I guess technically they could be, but not here. So they're just constants. the n is the degree. What's nice about these functions is the domain is all real numbers. There's no restriction, in other words. I mean, the range, that's a different story. The range actually, it turns out, depends on the n here. And I think the a sub n comes into play as well. Yeah, it does. I mean, it turns out if n is odd, the range and the domain are going to be the same. But if n happens to be even, such as if n is 2, in that case, you have a quadratic function. And we'll graph this in the next section. But if n turns out to be even, the range is not going to be the same as the domain. In other words, the range will not be all real numbers. That's a different story, though. I think to actually prove that, you need more advanced math tools, so that's different. Anyway, so if n is 2, we get what's called a quadratic function. And we will graph that in the next section. If n is 1, we get a linear function, as it's called. Well, in other words, we just get a non-vertical line. Okay. All right. If you divide one polynomial by another, what you actually get is a rational function. So a polynomial divided by another, that's called a rational function. And the domain there is all numbers such that the denominator is not 0. The denominator is not 0. That's what happens here. And now how do you find that? Well, to find that domain, you actually solve this equation first. You find all x such that q of x is 0. Those are the numbers you throw out. In other words, the domain will be everything else. I mean, we do it this way because it's generally easier to solve an equation than it is to solve an inequality. So let me say it again. Find the domain of a rational function. You set the denominator equal to 0, and you solve that for x. Right? So you have a polynomial equal to 0, and the domain will be everything else. We also have this function we saw shortly before. This function has domain non-negative real numbers. It's all x such that x is non-negative. Let me just pause the recording.